Okay, let's have a look at a chain of trust reference implementation and demo. We have used the Mars board from Embus Tech in this project, which offers an IMX6 dual-core processor running at 1 gigahertz. It also has 1 megabyte of L2 cache and 32 kilobyte of L1 cache, including the instruction and data caches. It has 4 gigabyte of eMMC on chip and 1 gigabyte of DDR3 SDRAM, and it also has 2 megabyte of SPI NOR flash, offering an SD card slot and much more which are not relevant to this project. In the first part of the demo, we are going to take a look at a system which is not secure. This means the U-boot and fit image are not signed and encrypted. Let's have a look at the case that the U-boot is not signed and encrypted on the target. We stop the auto-boot process in order to run into the U-boot prompt, and as we can see here, we have a version of the U-boot which is not signed and encrypted. We issue the have status command in the U-boot in order to get the security status of the device. We see that the secure boot is disabled on this device. And we have got multiple of hab events, including the event data that can be interpreted according to the hab API documentation in order to find the exact root cause of the problem. And also a summary including the hab status, which is a hab failure, the reason, which is an invalid address, and the context in which the problem has happened, which is the authentication context. For the next step, we want to modify the U-boot image binary. We have used Ghidra from National Security Agency (NSA), which is an open source reverse engineering tool. We import the U-boot binary. Then we select the architecture, which is ARM v7 Little Endian here. Then we open the imported binary and let the Ghidra do analysis. As we can see here, the U-boot is not encrypted. That's why we can see the environment variable in plain text and as part of define string here. So we try now to find the boot command. So as we can see here, boot command is run boot fit image. In a normal case, we switch to the byte view and we try to modify this. So we have to switch to the edit mode at the top right, and now we can modify the boot command. So now it's changed and our new boot command is hacked. Let's also change the boot delay. So we change it to 9 from 2 second. We save the modified project, and then we export the project as binary. Let's update the modified version of the U-boot on the target. So first we stop the auto-boot process and we check the boot command before the update, which is run boot fit image in a normal case. And we have 2 seconds for the boot delay. We reset the board. We have a script to update the U-boot. So we use this script, and as we can see here, the U-boot image is already on the SD card. We mount the SD card, and then we erase the U-boot partition on the SPI flash and check if the partition is erased properly, and then copy the U-boot image. So it's done. We just double check to see if everything is okay on the flash, and then we restart the board. So we already see the boot delay is 9 seconds, and the countdown started from 9, and now the boot command fails because it's not boot fit image anymore, but hacked, and also the boot command. As we can see here, and the boot delay is 9 seconds. Let's have a look at the case that the fit image is not signed and encrypted on the target. So we stop the auto boot process. We read the fit image from the SD card, and we use the image info command from U-boot to see the fit image contents. So as we can see here, the image 0 is kernel, image 1 is the FTD blob, and image 2 is init ramdisk. So we reset the board, and in normal case, the U-boot loads the fit image and the board boots completely. Now we want to modify the fit image. So similarly, we import the fit image binary to Ghidra. Then we select the ARM v7 Little Endian architecture. We open the project and let the Ghidra do analysis of the binary. Since the fit image is quite big, I'm gonna skip this time-consuming part. and directly jump to the point that, yeah, here, that we can see the defined strings are already decoded. And in addition, we can actually take a look at the binary contents using the function graph feature and explore the binary contents. And also there is so many possibilities. An example from this block, we can just click on the transitions to see uh, under which condition and to where the transition happens. So we switch to the byte view and we are going to just modify some stuff in the U-boot, in the fit image header, which is quite simple but destructive enough. So we make multiple bytes 0 and then we save the project. And then we export the project as binary. Let's run the modified version of the fit image on the target and test it. So the board is restarted and the U-boot tries to load the fit image, but this is not possible because it detects a bad fit kernel image format because we have already changed as part of the hacking process the fit image header. So we can also use the image info command of the U-boot to see what's going on. And as we can see here, we get a bad fit image format. And as a result, the device is not able to boot completely. In the second part of the demo, we are going to take a look at the system when it's secure. So this means the U-boot and the kernel fit image are signed and encrypted, and the storage encryption is also supported. Let's have a look at the signed and encrypted U-boot running on the target. We stop the auto-boot process, and as we can see here, we already run a signed version of the U-boot. We issue the have status command, the secure boot is enabled, and no hab events found. So this means the board uh, is booted in a secure environment and the U-boot image is already authentic. Now we want to read part of the U-boot image binary on the flash, and since it's just signed, we can read the text, the meaningful text there, and we have an environment variable that points to the U-boot image. Now we are going to change it to the signed and encrypted version of the U-boot and consequently update the U-boot with that version and test it. So now the U-boot image is U-boot signed and encrypted. We also have a script to update the U-boot and the flash. So we run the script. The update is done and we reset the board. Now we have the signed and encrypted version. We issue the have status command and we see the secure boot is enabled and no hab events found. Let's read again the U-boot image on the flash, and as we can see here, the contents of the U-boot image on the flash are not meaningful anymore since they are already encrypted compared to this case that we were able to read and interpret. Now we are going to modify the signed U-boots. We import the signed U-boot image into the Ghidra. Choosing the ARM v7 Little Endian architecture. We open the project and let the Ghidra do analysis of the binary. So since the U-boot image is just signed in this case, still the contents of the image can be interpreted, and we have to define the string as part of this analysis here. So we are going to just modify the boot delay. Now we switch to the byte view and try to find the byte that actually determines this 2 second of the boot delay. So it's there, and we're just going to increase it to 9 seconds. We save the project. And we export the project as binary. Now let's test the modified version of the signed U-boot on the target. We stop the autoboot process, and as we can see here, we already run a signed version of the U-boot. We reset the board. It's booting. And now we use the update script to update the manipulated version of the U-boot image. So the SD card is mounted, the U-boot image is read. We erase the partition and check if it's done properly, and now the copy process of the U-boot image is in progress. So it's done, and we just do a quick check to see if we have valid contents on the flash. And now we reboot the device. So the board is already restarted, and as we can see, the authentication process of the U-boot image is failing. That's why we cannot boot the U-boot, the modified version of the U-boot on this board. As the next step, we are going to modify the signed and encrypted version of the U-boot. Let's first modify the header. This is the part related to the boot data structures. As we mentioned in the presentation slide, it remains in plain text and it's just signed but not encrypted. We import the U-boot image. We select the ARM v7 Little Endian architecture here. And then we open the project. So the analysis is done by the Ghidra. And as we can see here, since the image is encrypted, there is nothing decoded. And we cannot see anything related to the defined string and the U-boot environment variable, which was the case in the signed version of the U-boot. Now we switch to the byte view and we're going to change multiple bytes in the image vector table. So we make multiple bytes 0 there. Then we save the project. And then we export the project as binary. Let's now test the modified version of the U-boot on the target. We stop the autoboot process, and as we can see here, we already run a signed and encrypted version of the U-boot on the device. We reset the board. It's booting. Now we are going to use the update script to update the signed and encrypted version of the U-boot, which its header is already manipulated. So as we can see here, we read the image from the SD card, we erase the U-boot partition and the SPI flash. We double check if the erase process is done properly by reading back the partition and the flash, and now the U-boot image is copied on the flash. So it's done. We just do a double check to see the contents of the flash, which looks okay, and we reboot the device. So as we can see here, the board is already restarted but cannot proceed with the boot since the U-boot image is already modified and the authentication process fails. Now let's modify the payload of a signed and encrypted U-boot image. This is the part which is encrypted using AES CCM and provides an authenticated encryption mechanism. So we import the U-boot image as a Ghidra project, and then we select ARM v7 Little Endian architecture. And we open the project. We let the Ghidra do the analysis. And as we can see here, since the U-boot image is encrypted, there is nothing meaningful decoded there, including the environment variables of the U-boot. So we switch to the byte view, and if you remember from the slides, we had from address 0 to C00 in hex the boot data structures, were which is just signed but not encrypted. But after that, which is the U-boot image itself, is encrypted using AES CCM. So we are going to change multiple bytes there, and we make them 0. We save the project, and we export the modified project as binary. Now we try this version of the U-boot on the target. So we stop the auto-boot process, and as we can see here, we already run a signed and encrypted version of the U-boot. We reset the board, and it's booting. Now we try to update this signed and encrypted version of the U-boot, which its payload is already manipulated. So we read the image from the SD card, we erase the U-boot partition on the SPI flash, we check if the partition is erased properly, and then we copy the U-boot image to the NOR flash partition. So it's done. We just do a double check of the contents, and then yeah, to see if everything is okay on the flash, and then we reboot the board. So as we can see here, the board is already restarted, but since the U-boot image is already manipulated, the authentication process fails and the boot cannot be successful. Let's have a look at this signed and encrypted fit image on the target. We stop the auto-boot process. We have an environment variable called kernel image pointing to the fit image that is used by the boot command. So here we have the boot command, and now we want to load the fit image from the SD card to the memory. Let's read some bytes of the fit image, and as we can see here, we have the signed and encrypted fit image, and the contents are not readable on the flash. So we put this fit image, which is signed and encrypted. So the device is booted. Let's go at the beginning to see what has happened. So we read the fit image signed and encrypted. It's already authenticated. The secure boot is enabled, and there is no HAD events found. And the kernel fit image authentication and decryption is okay. So let's reboot the board. We stop the auto boot process, and now we want to change the kernel image environment variable to the fit image, which is just signed but not encrypted. And now we want to read this image from the SD card and load it to the memory. Let's have a look at the contents. So as we can see here, the contents can be read and interpreted. Compared to the encrypted case here that we couldn't read the contents of the image. Now we run the boot command to boot the fit image signed version. So let's scroll up and go right at the beginning to see what has happened there. As we can see here, we read the fit image signed version. It's getting authenticated. Secure boot is enabled, of course, and there is no hab events found. And the kernel fit image authentication in this case was successful. For the next step, we are going to modify the signed fit image. So we import the fit image sign into the Ghidra, then select the ARM v7 Little Endian architecture. We open the project and we'll let the Ghidra do analysis. Since the fit image size is quite big, I'm just going to skip this part. So now as we can see, because the fit image is only signed, we have the defined string decoded as part of the analysis. So let's switch to the byte view and we are gonna do some modification in the fit image header, similar to the previous case that we had the fit image not signed. So we make multiple bytes 0 there. Then we save the project. And now we export the modified project as binary. Let's test the modified fit image on the target. We stop the autoboot process. We have an environment variable called kernel image pointing to the fit image, which is used by the boot command. Now we set this variable to the kernel image, the fit image which is signed and hacked. We do a double check and now we run the boot command. So it fails the authentication. Let's scroll up a bit to see what has happened. So we read the fit image, then the authentication is done, secure boot is enabled. The first no-hap events that we get here is related to the U-boot, but the second one related to the fit image has failed already and we get this hap event data. As we mentioned earlier, the event data can be interpreted according to the hab API documentation and the exact root cause can be found. But we have summary here that shows the status is hab failure, the reason was hab invalid signature, and the context in which this has happened is the hab context command. And at the end, we get the kernel fit image authentication and decryption error from our U-boot script. Now we are going to modify the signed and encrypted version of the fit image, the IVT header, the image vector table header, which is signed but not encrypted. So we import the binary into the Ghidra. We select ARM v7 Little Endian architecture here. And we open the project. We let the Ghidra do the analysis of the binary. And as you can see here, since the image is signed and encrypted, the contents are not readable. So now we are trying to find the beginning of the image vector table. We know some bytes of that because we have already dumped it during the boot process. So we are going to find it, and it's located at this address. So we are just going to modify probably one single byte there. Yeah, that's it. And we just save the project. And now we're going to export the modified project as a binary. Now we test this modified fit image on the target. We stop the autoboot process. We change the kernel image environment variable to the fit image signed and encrypted and the modified IVT header. And then we run the boot command. So the authentication has already failed. So let's see what has happened exactly. We read the fit image. The authentication is done. That was the IVT header that we have modified, and we have added this byte 65 there that we have already marked. The secure boot is enabled, but the hab authentication and decryption has failed. So we get the hab event data and also a summary showing the hab failure as the status, and the reason is hab invalid signature. And we get the kernel fit image authentication and decryption error from our U-boot script. And as the last step here, we want to modify the signed and encrypted version of the fit image, but this time the payload, which is encrypted according AES-CCM, providing an authenticated encryption mechanism. So let's see how it's gonna work. We import the fit image as a project into the Ghidra. We select the ARM v7 Little Endian architecture. And we open the project. We let the Ghidra do the analysis. And And again here, also in this case, since the fit image is signed and encrypted, we don't see any defined string as part of the decoding process, so nothing can be read. So we switch to the byte view and we try to modify something similarly that we did in the previous cases, just in the fit image header, because this is the part which is already encrypted as well. So we make some bytes 0 there, then we save the project, and finally we export this modified project as binary. So let's test this fit image on the target. We stop the auto boot process and we change the kernel image environment variable to the fit image signed and encrypted with modified payload. We run the boot command and the authentication and decryption process fails. Let's see what has happened there. So we read the fit image, the authentication is done, secure boot is enabled, but we get a hab event and also a summary there showing the hab has failed, and the reason was the hab invalid signature, and the context in which this has happened was the hab command context. We also get the kernel fit image authentication and decryption error from our U-boot script. In the last part of the demo, we are going to take a look at the storage encryption. If you remember from the slides where we were explaining the concept behind the black keys, we have the CAM keygen user space application which can create two outputs for us. The first is the blank key itself, which is used during the storage encryption, and the second one is the black key blob, which wraps the secret key used for the encryption and gives us the possibility to store it securely on the flash. Now we're going to take a look at the black key blob itself. So this is the contents of the black key blob. One remark here uh, is that the black key that we have used in this project is a 16-byte random key which is going to be encrypted using AES-CCN. Here we see the contents of the imported key from this blob which is used during the storage decryption. Now we are going to do multiple import from the same black key blob in order to see how the contents of this multiple import will look like. So it's the same blank key blob. We do another import. We check the contents. And we do one more import. And we look at the contents. As we can see here, except the key header, which follows the same format, the key payload is completely different among these three imports, since it's already encrypted using the AES-CCN. Here in this example, we have encrypted a partition on the SD card called MMC block 1 partition 4 at a block level using the decrypt. As a result, a new block device is created called encrypted_new here in the device mapper infrastructure. As we mentioned earlier in the slides, all writes to this partition and reads from this partition are encrypted. And it's mounted on the file system at this point /mmt /encrypted_new. Let's see the details of the encrypted volume. So we use a dm setup table show key command to see the details there. So as we can see here, the kernel crypto API uses the new cryptographic transformation registered by the CAM driver, which uses the black keys for this encryption and decryption purposes. So we have the size of the key here, which is 48 byte, and the type of the key added to the kernel keyring, which is logon key here, and the key name, of course. Now we create a new file in the mounting point of the encrypted volume on the file system called test. We echo some text in it. And we read it back. Now we unmount the encrypted volume mounting point on the file system. Then we remove the encrypted volume itself from the device mapper infrastructure. And of course, we cannot have the encrypted volume on the device mapper since we have already removed it. And we cannot access our test file anymore. Now let's try to mount directly the SD card partition at some point in our file system. So we create a directory called test. We try to mount the SD card partition on this folder, but of course this is not possible. And we get a file system error since the SD card partition is encrypted and mapped as block device in device mapper infrastructure. And this cannot be accessed or mounted outside the device mapper infrastructure.